All right, so let's take a look at the different kinds of problems. This is our first of 5 review sessions. And I will try to every one of them will be posted, so if you need to come back and go through them again, it's great. I also have the years that they are, so if you ever need to reprint it out, like I want to do this from scratch, although usually once you do something, it's kind of hard to fake that you've not seen it before. But these are questions, hopefully, that you feel will be helpful in the long run. So away we go. First one is an equilibrium problem. It's really important. I try to, do an equilibrium problem every single review session because they're on the test. It's just going to happen. So I'm glad some of us brought paper to a review session. Here we go. Good. See, Tyler's got this whole, he's going to find something. You need water in a canteen? You probably have. I got 3 beakers. Beaker 1, Beaker 2, Beaker 3, HCl, NH3, and NH4Cl. So they're probably going to be utilized at different times. Each of these 3 beakers contain 25 mils of a 0.1 molar solution of those, each at 25 degrees, so it's not different temperatures. A, determine the pH of the solution of Beaker 1. Justify your answer. All right, so away we go. Keep doing it. Okay, so if I take a look at that, why can I do Beaker 1 and only Beaker 1 without really seeming to have a lot of information? It's a strong acid, right? So I'm making little notes here, but this is a strong acid. So please at least set it up, but if you want, you can calculate it as well. Again, today it's about you doing it as well. It's not just me giving it to you. It's important that we execute and get the answers. It feels good. It gives you good confidence when you see that answer sitting on your paper that I have on my board. Please understand, most calculations assume 2 points. I can't promise you that. Assume 2 points on a lot of things. One is for the setup, one is for the answer. Not always. And unfortunately, I don't have the scoring guidelines today. I must have misplaced my sheets. So I'm doing these answers kind of with you right now. So that would be kind of the setup. Obviously, for most of you, if you've done this enough, you probably could have guessed this without a calculator. Right, because 1 times 10 to the negative whatever is that pH, that exponent. So this would just be, hopefully you got this, hopefully you wrote it like that. The pH, please have 2 digits after. How many sig figs is that though, 2 or 3, technically? Technically 2. With pH is it's only the digits after the decimal point. pH is different. So just understand that, but it's not a huge deal. But I have seen problems go out of their way, literally saying write the pH with this many sig figs. They want to see if you understand that. So if they do that, just be careful. All right. So we move forward. Letter B. Let's take a look. It says in beaker 2, the reaction NH3, so ammonia plus water, gives the ammonium ion and hydroxide ion occurs. The value of Kb for the reaction, or for NH3, is 1.8 times 10 to the negative fifth. I. Write the Kb expression. So please, write the Kb expression for I. And then, if you want, calculate the OH concentration in the solution. If you're not sure about that, we'll get there, but you should be able to get at least I. Get that expression done. What would that look like? Brackets or P's? Brackets, right? Brackets. There's only one that uses P's. Everything else is brackets. Everything else. So, the one big thing, hopefully as you did this, is that you left out the water, right? Because water is a liquid. And we don't want that. Water is a liquid. So that is I. Again, just make sure you leave that out. So, double I. This is where, if you remember and you have knowledge on this, you're in great shape. If you're forgetting it all, my suggestion to you, if you are doing anything with K and you're hesitating, at least start an icebox. Worst case scenario, you're like, oh, I'm good. I got it. If you're forgetting. So let's just talk about that. I'm going to do it right under here, just to kind of show you what I'm talking about, because I don't have a lot of space. You have unlimited with your paper. But it says calculate the OH. If you're confused by what that's asking, take a look. So I have 0.1 molar of NH3, sorry. So I'd have, like, this is my icebox. I have 0.1 molar of that. This one count, right? This would be my double line. And then what are my NH4 plus and OH minus right now? Those are zeros, right? So when this is all said and done, what am I going towards? This is x squared over initial minus x, correct? Sometimes you don't see that right away. Sometimes you have to see that setup, okay? And even this, like the plus x and plus x, oh, well, what are you looking for? You're looking for OH. What is OH minus going to be in this, in general terms? X. You may not have recognized that when you started. So if the icebox can get you to the idea that, oh, OH is going to be X, awesome. Now I'm good to go. I can go forward. So I have 1.8 times 10 to the negative fifth equals x squared over initial minus x. X is going to equal concentration of OH minus, and I'd like you to solve for that. But that's the setup. We haven't done that for just a little while, so it's good to review, but that should come back. What year is this from? When does it say?
2011.
Okay, so this isn't that much ago. I know it's 6 years, but to me that doesn't seem like a lot. One day this is. 1.34 approximately times 10 to the I guess they're all right. And I box it. If I have an answer from the calculation, please box that. Again, I'm sorry I don't have the points today, but I'm going to assume that's 2 points. One for the setup, one for the answer. It's just the way it usually is. Okay, so good. Again, these are worth big points. This isn't like, oh, this is a little problem. This is a big problem. Let's talk and move forward. Letter C. In beaker 3, so they keep moving down the table here. You have ammonium with water and ammonia and hydronium ion. I, calculate the value of Ka, and then double I, the contents of beaker 2 are poured into beaker 3 and the resulting solution is stirred. Assume that volumes are additive. Calculate the pH of the resulting solution. All right, I'm going to give you a moment. Go as far as you can. You should be able to do I pretty quickly in comparison to double I. If you're not sure how to do double I, we can talk, but I'm going to give you a moment. So I'm going to pause this and see where we're at. All right, let's take a look at this. So CI, usually I's, remember this, I's, double I, triple I's. I like I's more than A's and B's and C's like by themselves because usually they're smaller things that are broken down and they're really directly linked. So it actually gives my brain a kind of a roadmap and connects it like, oh, well, those must be related, or I'm going to use that for this. And they're just trying to get points out of little parts of it instead of just having an open-ended problem. In general, the test questions I have given you throughout the year are much harder than these. The reason why is I didn't break these down all the time. I was just like, go, like find the pH, please. And I didn't ask for all these little things. But this actually breaks it down. Like I would never just say calculate the Ka. Like I would just make you find that and assume you knew how to do that. So these are good. I love I's and double I's. I think usually I can try to maximize my points. And if not, it's such a small amount that, please, big hint. If you're not sure how to do one, but you're like, I think I would do this process for the second part, then assume something for I. Assume this value. So then you can at least use it in the second part. But those don't always carry through to the next parts. So I's, double I's, triple I's, those are going to be linked. So how do I get Ka? I need to use Kw, right? It's however you want to write it, but I would have written it like this personally. And we've done this one a lot. Now I can't remember what it is. 5.6
Yeah.
times 10 to the negative 8th. 10th, I mean, 10, I meant. Good. All right, so there I am. And that's probably 1 point. That's I. Now let's talk about double I. Okay, so reminder, this is not a coincidence. By giving me the equation, I might need that. I'm just going to do that once, especially for the sake of review here today. So that's the equation that I'm given. It says, double I, the contents of beaker 2 are poured into the beaker 3 and the resulting solution is stirred. Assume that volumes are additive. Calculate the pH of the resulting solution. Okay, so I had 0.1 molar of NH3 and I had 0.1 molar of NH4 plus, right? That's the plus right there. So here's the thing. It says assume volumes are additive. So technically, yeah, you probably would have to figure out if you're doing something like a titration, you have to figure out how many moles you have and then recalculate over the new volume. The thing is, it's in the same volume with the same molarity. So even if I add the same amounts, are these not going to be still exactly, they're still going to be equal, right? Like they're going to be equal because they're the same volume and the same molarities. So when I'm taking a look at something like this right here up in BI, it's a similar problem. This is where we've been graphing some ideas to this problem. Let me show you. If I have, and you don't have to write this down if you don't want, because some of you are like, I did something different. That's great. But I just want to visually see this one. What happens with this? These two are equal, right? So what am I dealing with? Anybody know the pKa? The pKa. Easier way to remember this in general, and I hope maybe a lot of you went towards this. When I have amounts of the conjugate partners, that's Henderson-Hasselbalch, right? That's where I was hoping you'd go. But you could also do this. And then go, well, I have the same amounts here. Well, those equal each other. Well, if I take negative log of that, that's pH. If I take negative log of H3O plus, that's pH. And if I take negative log of that, that's just Ka. Well, the question is, what is the pH? So I can do Henderson-Hasselbalch, and that's what I'm going to do. So I take negative log of my Ka, and then it really doesn't matter how I do this, because isn't that going to be the same? The values? No matter what, they're the same. Even if you'd argue that these aren't the same volumes anymore, or molarities, they've been diluted, I understand, but they're the same. And what's log of 1? Big 0. So that's basically all gone, so it's just negative log of my Ka, one way or the other. This is a perfect buffer. Either way. 9.25? Anybody? Okay. So, if you got that right without any help from me, there could have been a couple angles that you went. It could have been through this idea right here and recognizing that. But to me, the one thing that I always go right back to, and I think is a really easy equation, as complicated as it might look, if I have amounts of conjugate partners, I can plug that into Henderson-Hasselbalch. All right, finishing up with those ideas then. Letter D. Says the contents of beaker 1 are poured into the solution made in part C double I. The resulting solution is stirred. Assume that volumes are additive. Okay. So now this is a little different. So you need a little bit more. So okay, first let's get this equation right. So let me see if you can get the equation. So this is the equation initially, and now I'm pouring beaker 1 into that. So what is beaker 1? It's HCl, right? So beaker 1 is bringing HCl to the table. That's H+. Okay? To this day, I bet most of you would admit, the hardest part for me is writing an equation. Okay, that's an acid. Acids react with bases, right? So what has to be right here? Nope. What? Because that is a weak base, right? It's got to react with the base. Remember, strong acids and strong bases, only one part's reacting. The strong acids, H+, the rest of it's gone. Strong base, the OH is there, the rest of that is gone. It's just going to go as a salt. So if I make that, what's going to be on the other side? NH4 plus. You still need all the active participants, and we have all those. We have all those right now. Okay, so here's the tricky part. And I think this is a little confusing. It says the contents of bigger 1 are poured into the solution made in part C double I. The resulting solution is stirred, assume that the volumes are additive. Okay, so you have a certain amount of each of these, okay? You have, what is this, 0.1? Yeah, 0.1. Just write that down. I have 0.1. What did I start with? They're all 0.1s, right? In the beginning? You're like, what? We'll worry about the moles in a second. Which way does this have to go? We always need positives and negatives in their x's. How do I know it goes to the right? I love when I push a color and it doesn't. Strong acid. Strongs always go to the right. Like it will take whatever it has with you. It's a bully. So, what that means, right? That's what that means. Okay, so obviously zeros. And here's where, unfortunately, you're going to make a little bit of a mistake, potentially, is that, and I could have done this in a couple different ways, but maybe I should build this before. You need to take into account the fact that it says, assume the volumes are additive, okay? So I'm going to give you a little head start, and then I'm going to pause and just see if you can figure this out. Just give you a minute and a half, 2 minutes. Are they all 25? I don't want to scroll. Is it 25 mils each? Or am I wrong? Yeah. Okay. So they're all 25 mils. How do I use that? Now, maybe I went too far. Maybe I did it too quickly. But most of us would have all done the molarities right away. So give it 2 minutes once, or a minute and a half. Just think to yourself, what do I need? Here's the trick, is that it's asking for, before I give it away, but it says, is the resulting solution, oh, I'm sorry. Oh, I'm already jumping double I. I'm sorry. Calculate the final concentration of NH4. So I need to find the final concentration. That's not right. We'll talk about that. But before I get into there, my apologies. I, is the resultant solution an effective buffer? So you got to say, I'm sure it's a justify. Why isn't it an effective buffer? You don't have a pair any longer? A word consumed is good. What was consumed? What matters in here? If I was going to make a red line underneath things, what would go under, which ones would I underline to say that would be part of my effective buffer? NH3 and NH4 plus, right? So my NH3 has been consumed, right? And then that would actually probably be enough, which makes it an ineffective buffer. Or I don't, because my NH3 is consumed, I do not have conjugate acid-base pairs. That would be a really good answer. Does that make sense? Like you need both, right? You got to have both. If you only have one or the other, then it goes all the way to being more of an acidic or basic solution that can get affected really easily. You need a little bit of both so it can help consume it. Okay, so that was I. And I'm sorry, I just saw it double I right away. Give it a shot. I'm going to pause it. Just can you figure out, maybe I went too far, maybe I didn't. How do you find the final concentration? Remember, volumes are additive. All right, give it a shot. So ultimately, let's say you did it this way, which I purposely started it like this. I'm not trying to confuse you at all. Here's my issue. This is fine, because no matter what, however many moles I have of this, they were going to equal. So what could I have done? The easiest way is to do this in millimoles. You take the molarity and multiply it by the volumes, and you have millimoles of each. They'd all be equal. Okay? But you need millimoles here, because when you're all said and done, if you want a final volume of this, a final molarity, you need your moles of your NH4 plus over what? Your total volume. So what I'd suggest is, what is that initial value? Okay, whatever that is, Clearly, that's what you're adding because it'd be the same amount. So did anybody figure it out? Well, how many millimoles do I have? Because that's the easiest way to do this. Well, in the beginning, on all these, 2.5. Because 0.1 times 25 mils, right? So let me just do that on the side. If I had 2.5 millimoles, would we agree that these would all be 2.5? So then that would be minus 2.5, minus 2.5, and this would be plus 2.5. The only column that matters is this one, right? Because that's the one that's going to actually have something at the end. So this now should be like, oh, yeah. You can't just go, oh, 0.1 plus 0.1 is 0.2, and you leave it like that because they are going out of their way saying the volumes are additive. So then what I have to do is put that over 75 mils, correct? Because it's from each one, right? Each one has 25. So my final answer is roughly, correct me if I'm wrong, is 0.0667 milliliter. I guess to me, the other gut feeling you should be is like, wait a minute, even though I gained some, I shouldn't have more than I started with. I'm diluting this 3 times over. Right? That's a lot. So that would be the final volume. And that's the end of that problem. As a whole, if you take a step back for a second, you're probably like, I could probably handle that. Good. And if you can't, we got to keep working on it. So that was an equilibrium problem. It's a couple years ago, but it's a really good one. And not a lot of people did very well on it, which shocks me because I think that we can handle that. Okay, let's go to our next problem. So this one is touching a little bit more on free energy thermodynamics. Always shows up somewhere, somehow. Sometimes it's its own problem. Usually it's intertwined within problems. So you kind of have to get the idea here. So here we go. Answer the following questions about glucose. And it gives you a formula, an important biochemical energy source. A, write the empirical formula of glucose. This is first year chemistry stuff. Do you remember or know what the heck they're saying? So if you do, great. If not, then you're just going to have to wait. So if you know the empirical formula, please give it a shot. I hope you know it. Simplest whole number ratio. Please, when you're done, do me a favor. Whenever you do an empirical formula, just double check and re-ask yourself, can I simplify that? You'd be amazed. You get something in your head like, I will divide that by 2. And you feel good about it. You write it all down, and you move on. You're like, oh, I could have divided all that by 3. So you should have divided it by 6. Just common mistakes that people make. You got to make sure that you're taken care of. That's probably just the point, but you know how to do it. So that's just some vocabulary. Okay, in many organisms, glucose is oxidized to carbon dioxide and water is represented by the following equation. So you're going to probably need to use this. A 2.5 gram sample of glucose, and excess oxygen replaced in a calorimeter. Oh gosh, I don't like calorimeters. Well, let's see where it takes us. After the reaction was initiated and proceeded to completion, the total heat released by the reaction was calculated to be 39.0 kilojoules. Notice it doesn't say per mole. It's important. It says that's the amount that it was actually released. Again, I don't always know how to do some problems immediately until I start looking at units, and then it kind of unfolds itself. So B, calculate the value of change of H in. When they tell you, they go out of their way, they're not even saying like in parentheses, they actually say do it in this unit. That's a hint to me for the combustion of glucose. So this is the combustion of glucose. I want change of H in kilojoules per mole. Well, let's talk about what we have. You can look at this problem. Most people will wilt on a problem like this. I have grams right here, right? And I was given kilojoules. What I need is kilojoules per mole. I'm already in one of those, so it should make sense right now. Hey, let's get this one into moles. Let's start there. Even if I don't know where to go completely, let's start there. So I'm going to take 2.5 grams I just thought of this, but I could totally see somebody now using the empirical formula for this and totally getting worked over. Like, no, I used the CH2O. I believe that's 180. Anyone want to quickly do that for me? 180? Okay. Evelyn knows. Okay. Please do yourself a favor. Do not round too much too early. Like, don't cut off too many numbers too early. You can always go down to 3. You can't go back up. Okay. So, does anybody want to tell me what they think they should do? Let me tell you this. What that's saying is that's how much glucose in moles, because that's actually an amount. Grams is an amount, so is moles. That's how much was combusted. It wants to know what is the kilojoules per mole. Huh? Perfect. Yep. So what it's saying is I use this amount right here, and this amount of kilojoules was released. It wants to know, guys, this is a generic amount. When it says kilojoules per mole, that's generic, because then it's like, hey, for every 1 mole, this is how much. This is specific. This is how much I actually have, and that's how much came off. So all I need to do to finish it off is kilojoules per mole. So change of H is going to equal 39.0 kilojoules per 0.01389 moles. Does that make sense? Like, I didn't know maybe I needed to go there right away. Just slow down. Okay, I don't have that unit, but I can get to that unit. All right, I already have that unit. Now, how can I utilize those? It's not that complicated if you break it down. Most people never see it, though. They just don't see that. You just got to slow down. So, I get a lot of room. I know this isn't great with sig figs, but I'll just leave it like that. 2808 or so. Now, last little thing. And I don't know if you get knocked, and I'm really sorry. I feel bad I don't have the actual answer sheet, but I feel good about all of our answers. So calculate the value. It says total heat released was this. So, anything technically not quite right on this? Just one thing. Should be a negative. So, either you could have, if you wanted to place it there because of the word release, where it is, I just saw it right here. So technically, I wonder, change of H itself per mole is important. A sign does matter. It did not ask for just how much was released. That's different. If I ask how much was released, I don't need a negative. But if it's just saying what is the change of H, a negative is important because it was released. Okay? I will tell you that tomorrow. I'll look it up for you. I would fear there could be a chance. We'll take a look. But when in doubt, when oxygen is not available, glucose can be oxidized by fermentation. In that process, ethanol and carbon dioxide are produced, as resulted or represented by the following equation. So see how they have the change of H in there as a negative. Here we go. Bunch of I's. Again, I love I's. We'll just do it right down here. I. Calculate the value of the standard free energy change for the reaction at 298. Include units with your reaction. What? Okay. So, how do I do that? Anybody just, I'll do it with you right now, but what am I going to do? And if you want, you can use your own sheets today too, because that's what you have in your test, but does anybody remember in general? I guess I didn't read something. It says the value of the equilibrium constant Kp for the reaction at 298 is 8.9 times 10 to the 39. Anybody remember? I think that's right. I don't have it in front of me either. I don't know if there's a plus. I think that's right. So whenever you're doing with free energy and then you're given anything with kind of a K, that's what you use. So all you need to do is plug and chug. Almost all free energy thermodynamic stuff, guys, is plug and chug. You just have to make sure you're plugging and chugging the right stuff. Are you doing products when we reactants, or are you plugging it into an equation? So in this case, I am plugging it into this. Let's talk about what I know. So first, all energy needs this R value. Frankly, suck it up and write the units. It's on the sheet. Just do it. I don't know if you can get docked. I can't answer that question. I don't know. But it's not that big of a deal. All of these values are always at room temp, which is 298. And then they give you the K as well. And that is just plugging it in. Now, your final answer right now is in joules, so please be careful because it does say include units with your answer. It doesn't say specific units, so if you want to keep it in joules, that's great. Usually tens to hundreds of thousands, you convert back to kilojoules, but that is not a hard rule. You don't need to do that. You can definitely have a little variance with that. Like negative 228, like 228,000, something like that. Sig figs, it is important. So to be honest, going to kilojoules is easier. If you forget the moles, it's not a big deal. And I know technically it's moles. Why do I go to the kilojoules again? So then I don't have to worry about the other digits. I can just get rid of that. So that's an appropriate answer. If you have it off slightly from mine, you're probably right. Double I. Calculate the value of the standard entropy for the reaction. What do you do for that? Anybody? We just talked about all these, so think about what you have now. Anybody know? What's your gut telling you? Nothing? Oh. Yes. Well, I don't get it. What do I know? Well, here's my G, right? And what else do I need? Where's my H? It's right there. It's within the problem. Please understand that it can be given to you. What do I have to make sure I do? Use the same units, right? And they've gone out of your way to say this better be in joules. You don't get a choice then. There's no choice there. They told you that's what they want. So you have to convert your free energy into joules. So please plug that in, calculate it up. And it is important to make sure that you use the right units. And I know it says Kelvin times moles. It's not a big deal. So around 537. You'll get it wrong if you just put the wrong units. So make sure that you have everything. Geez, that's only double I. Got a lot going here. Notice they all link. In I's, double I's, triple I's. That's good. Indicate whether the equilibrium constant for the fermentation reaction increases, decreases, or remains the same if the temperature is increased. Justify your answer. I would love to hear why someone believes one way or the other. So, if I have a indicate whether if the same temperature is increased. So I increase the temp. Will the reaction increase, decrease, or remain the same, or the equilibrium constant is? So obviously it's got to do something. So first off, temperature can affect equilibrium. It's not a blanket statement. When I increase, it goes this way. When I decrease, it goes this way. Anybody want to add a little knowledge to this? What do I know? Temperature deals with heat, so that is the great question. Which one deals with heat in heat flow. Enthalpy, right? Entropy is disorder. Okay, so it's that guy. So what does that tell me? Go to the basic. What is it? Exo or endo? It's exo, right? So what does that mean? Where's my E? It's on the right, correct? That's what you have to envision. You have to envision that the E is on the right. So, if I increase the temp, where is it going to go? It's going to drive it to the left. Now, make sure you answer the question, because sometimes it's like, will this thing be increased or decreased? I can't remember again. Indicate whether the equilibrium constant for the fermentation. So equilibrium constant. Well, if it drives it to the left, the equilibrium constant will go up or down. So if it drives to the left, I'm going to make more of that and less of this, right? So it should go down. Should go down. And even if you're like, and I get it, you're like, yeah, but that's a solid. It's a solid. That's not in the equilibrium constant. Fair enough. But it's still going to make less on the right. Right? It's still going to make less. So the whole number gets small. So the answer is it will decrease. And this is, I love this answer. I don't love it, honestly, but this is what I don't have the answer sheet in front of me, but this is how I would say it. The equilibrium constant would decrease because the reaction is exothermic by increasing temp. Drive the reaction or it will produce less products, more reactants, or anything else like that. I always am. That's always hard for me because basically you just say you assume it then. Hey, when I increase temperature and it's exothermic, it drives it left. Well, you have to have some sort of a trick or understanding about why it does that. So that's what and where that E comes into play. Okay. One more on this one. These are the two longest ones of the four we have today. Letter D. Using your answer for part B. Well, we're going all the way up. So that means whatever you have, use it. If you had nothing, assume something. Is that on here or did I cut it off? It's on there, right? Letter. Okay. Sorry, sometimes I cut off certain ones at the end. And the information provided in part C, man. Calculate the value of change of H for the following reaction. Okay. So let me say it again. Using the answer for part B and information provided in part C, calculate the change of H for the following reaction. This is where students never see this answer. So this is what it's asking. For this reaction right here. And I know you have it right in front of you. Anybody sensing what this is? Hess's law. How did you know? How did Tyler know that? Whenever they give you a new equation at the ending of problems and they're talking about change of H at all, and it's like, it's close to the equations I've been looking at, it's pieced together with some other equations. Man, well, that equation has this part, and this equation has that part. If there's multiple equations that all seem like they have a lot of sharing, and you're asked to find a new enthalpy, it's always Hess's law. So what you just need to simply do is take the equations that you know, and you need to either multiply or divide, or you need to flip them. And then you need to add those amounts up. Okay? So for example, this first one, I'm going to write these out, and I don't know if it actually makes you do your work. But this is the first equation, just so you can visually see it. And we found it to be this. Right? I'm sorry. Negative 2808. I'll write it on this. Usually it's on the right side. I'll do it on the right side. And then here's the second one. fermentation. And we just figured out, well, it says it on there. What does it say? Negative 68. Please make sure you're in the same units. Okay. So what I want to do is basically get it to equal the one in the blue. Right? That's what I want. So I took the equations, and now I need to make sure that I'm flipping up. Units or states of matter are important. So sometimes water comes into play, like, oh, it's all the same. There's only one water, so I'm not really worried about it. So if I just take a look at this right now, do I have to flip anything? So find something that's unique. That's what I always do. So, and if you're really stuck, and I'm not saying that you guys are, but like, I need that one, right? Because that's in here, in the blue, right? I need oxygen. I need CO2, which that's confusing. So I'm not going to underline that one, and I'm going to underline H2O. Why didn't I underline the CO2? Because it's in both sides. But the fact that they line up, I'm just looking at the blues with the greens, and they're on the proper sides, it does not look like I need to flip anything. It's about magnitude now. So if I flipped it, I hope we agree though, I do flip it, these would become positive. Right? So what do I have to do with that first one? Anything? And again, don't look at the stuff that is going to be canceled. Look at the things that you need. Like it's only by itself. So I look at that. The only thing that really counts for me is either the oxygen or the water. Did I accidentally flip it? I did. I'm sorry. I did flip it.
Yeah.
My fault. I'm sorry. So, right away, then what happens to that one? This is actually where it should be. Good call. Thank you. So that becomes that, right? Good call. So that's flipped, and it's been flipped because this was the big key to that one, right there. Like that's what jumped out, right? So what do I have to do this first equation? Let's just finish this up so we can get the last ones. What's my magnitude? Multiply it by half, isn't it? I need 3's and I have 6's. We always multiply, you don't divide. So that's multiplied by half. So this is 1/2, correct? This is now 3. This is 3. This is 3. And then
You don't have any coefficients in this equation. CO2, it's 2C2H1. It's 2C.
here and here. I don't know what I'm copying from. What do I have to do with this one? Besides already flipping it, thank you, again. I have to have that as well, right? Because I see this, the C2H5OH is the biggest thing to me. Otherwise, I need to also cancel some things. I need to get the glucose down to 1/2. So they're both halves. And we have spent a little too much time. But here's a 1, here's a 1, here's a 1/2. So then I got to take this by 1/2 as well, and this by 1/2. So when it's all said and done, I take 1/2 of each of those. You add it up. I do not have the calculation, but let's get it right now. So I take negative 208 times 0.5 plus positive 68 times 0.5 as well. Obviously, the math is not all that tricky, but you want to make sure that you can get it right. Correct me if I got it wrong. Negative 1370. Anybody else get that? So we had to cut them both in half and flip one. So Hess's law. And I know we're going to run over just a little bit. That one took a little too long, but the next two go faster. All right, so that is a equilibrium or thermodynamic problem. All right, we have not seen this for a long time, so here we go. A little electrochem. This one's a lot shorter than it looks. So here we go. Be ready. They're giving an equation. It's a redox. I know because there's charges moving around, and one has a charge and then it doesn't, and the other one doesn't have a charge and then it does. So that's redox. We'll revisit that very, very shortly. A, write the complete electron configuration for Zn2 plus. So first, you do need to ask yourself, how many electrons do I have? So if you look at zinc, it's number 30. So 2 plus would mean 32 or 28. 28. Very important. Very important. Now, You got to be smart about this. When you cycle through here, where are the electrons take? So they're being removed, right? They're taken away from the most outer electrons. So right now this ends at 3. Anybody know? 3d10. That's where that is ending. But that's not necessarily where the electrons are being taken. So as I write this out, I have 1s2, 2s2. For sake of time, I'm going to do some of this. And if you need some refresher, we'll get some. What comes after 3p6 when you're actually filling this out? And if you're like, I don't remember, you use the periodic table. 3p6, I'm lying right now at argon, right? 3p6. So I jump back down, and what is the next thing I would write? 4s2. No, don't write that. Because what happens is you got the three p's and the 3 s's here. You go up, and you got the 4s2, and then we come back down to do the 3d's. Which ones are the ones removed? The outermost electrons. It's always the outermost. It's not the last. Because they're the ones that are exposed because they're the furthest away from the nucleus, right? It's the easiest to remove. So the answer is this, and the order does not matter. But that's the answer. It's not 3d8. Okay? It's not 3d8. It's important. That's why they asked this. They're hoping that, not hoping, but they think you're going to do 4s2 to 3d8. Okay? So you always remove the outermost electrons, the valence electrons. I hope that makes sense. Letter B. Which species, Zn or Zn2 plus, has a greater ionization energy? Translation, more difficult to remove valence electron. So, which one? The Zn or the Zn2 plus? By the way, the Zn would have this. So who has the greater ionization energy? The Zn2 plus. Why? Because you got the 3, you got the 4, you got the nucleus. This is your Zn out here. This is your Zn2 plus. It would be more difficult to remove it closer to the nucleus than further away from the nucleus. So the answer is Zn. Does that make sense? I mean, we haven't done this for a long time. So this is one of those things we do want to definitely look. Oh! More difficult, more difficult. So because this is closer, more difficult. I think you said Zn. It's closer. If you need to make a little extra note, if the electrons are closer, it's going to be more difficult to remove. Sorry about that. Letter C. And right now it's like, wait, this isn't even redox yet. Yeah, there's not a lot in this. Identify the species that is oxidized in the reaction. Okay, you can use a lot of knowledge in here. Oxidize. Oil rig. Oxidize. Oil. Oil oxidation, right, involves loss. And what is loss? Of an electron. You can always, I still use it in my head. I'm like, okay, wait, hold on. All you need to do, we could talk about it in this drawing. I could do 10 minutes on just this drawing and talk about all the different moving parts. Look at the equation, okay? Which species is losing electrons? So it's either Al or Zn. That's the answer, by the way. It's one or the other. So all you got to do is look on the other side. Which one has lost electrons? Which one's going to lose electrons? Al. It went from, the answer is Al. And the technical answer, Al solid, that's the one that's losing it. It went from an atom to a positively charged ion. So if you're positive, it means you lost electrons, right? What did the zinc do? It went from a 2 plus, missing 2 electrons, to just Zn, so it gained its 2 electrons back. So that's redox. But that's, sorry, not, yeah, it's reduction. But not redox. Redox is both. It's been a while for me too. D. The diagram includes a salt bridge that is filled with a saturated solution of KNO3. Describe what happens in the salt bridge as the cell operates. Okay. There's no getting around this one. You need to explain a little bit. So if you can try to figure this out, it's really good. Who's gaining the electrons? We just said it. They're losing it. So zinc's gaining it. So the electrons, just draw this on your sheet. Electrons are, or even on a generic picture, electrons are going that way. Let me try to explain then what's happening, because it's important. If you're losing electrons, that means that the Al, look at, and I can get it all from this equation. The Al is becoming a solution, right? So the Al is going into solution. The zinc is becoming a metal, so the zinc is going into the metal. So the minute I notice that, I can describe what's happening in the salt bridge. You have to specifically say what ion's going where. I'm gaining positives. So which of these two ions is traveling towards this? Remember, we always want to regulate. We always want to balance. So who would go over there to offset that? The NO3. So what you would say is the NO3 minus would be traveling or moving towards the aluminum cell, the Al cell. So the NO3 minus, you can say it moves left or moves to Al cell, and the K plus, and again, you could say left or right, but I hope this makes sense. I'm losing positive charge, so the K plus offsets that positive charge loss. Notice how I figured that all out just by looking at the equation. Like that helps. Okay? So if it ever asks what's actually happening in the salt bridge, even if it doesn't go out of its way, you need to say where the actual ions are going, please. It's important. Okay, a couple more, and then we're done with this one. And I'm going to be probably 10 minutes off. And as always, if you have to leave, you got to leave. But I don't want to cut any of this short. Letter E. It says determine the value of the standard voltage in the cell. Okay, first, I just want to say this. Values would have to be given. And this was when, if you remember, some of you keep trying to use the little half sheet, and I really appreciate that idea that we only needed it once. Like, it used to be on a sheet. Hey, it's a positive for you. It used to be just on a sheet, and then you'd have to be like, do I need that? And then you'd always wonder if you needed it. Now, they go out of their way, and they just give you the values. So they're like, oh, I need that now. All right, so I'm just going to give them to you. They would give you reduction cell potential values, and what you need to do, just write this down. And this will hopefully make sense. This is what would be given to you. I'll break it down for you. They always give you reduction. Oh, what do you mean reduction? Reduction involves gain. I'm gaining electrons. This is a redox problem. What does that mean? One of them has to flip. How do I know how to do that? You always maximize your voltage, right? And by the way, if you even just look at that, which one's not correct? This one has Al on the left and Al3 plus on the right. Oops. That's been flipped, right? Do you see that? Like I could have flipped this one. This one needs to be flipped. Because of that, what happens? That becomes a positive. That's it. Well, I have to multiply it or this or that. No. Well, the electrons aren't equal. I understand. That doesn't matter. The voltages, all they do is flip for signs. So the final answer would just be simply this. But please understand that you have to be given those. And this is how they would give it to you. They'd give you both like that. They wouldn't flip one of them for you. If you're like, I don't know which one to flip, you have to understand that it's going to maximize the voltage. You can also figure that out, though, based on the actual equation. Both would work. Okay? F. We're almost done with this one.
Why don't you have to make the electrons
It just doesn't work that way. It's not Hess's law. Indicate whether the value of the standard free energy change, G, for the cell is positive, negative, or zero. Oh, I'm going to use an equation. No equation needed. This is a battery. I plug a battery in to something. Does it start to work? Yeah, it does. That's what the battery does for us. So, what sign would G be then? Negative?
Wait. That's positive.
But isn't the battery the thing that's getting it started? You're plugging in the battery? I'm taking my thing and I'm putting a battery into it and it works. My flashlight, put a battery in, turns on. So, is it working? It's working. The battery's causing it to work, right? Let me give you a hint. If it ever says voltmeter, That says spontaneous. That means this cell is a working battery. If up here it says battery, you're like, wait, what? Or energy source. Then that means that it's actually driving it the other way. It's going against nature. So that's non-spun. It's recharging a battery. That's causing it to gain energy, not losing energy. So a battery naturally will occur. If a voltmeter is there, it's just seeing how much energy exists. So if it's naturally happening, then it's spontaneous, and that would mean that change in G is negative. Because it's spontaneous. That's what you can always say. The sign is negative because it's spontaneous. And lastly, and then the last ones we'll go really quickly through. I hope that makes sense. Like, you can literally just look voltmeter or non-voltmeter. Voltmeter or energy source. Oh, energy source. Well, I'm plugging that in, so I'm making it work. Well, battery is naturally giving me the energy it has. If the concentration in the Al3 plus half cell is lowered from 1 to 0.01, does the cell voltage increase, decrease, or remain the same? There's a lot of ways you can think about this. So you could sit here all day and go, okay, so that's lower, and the electrons are going like this. So is that causing it to drive here and there? There's an easier way. I lowered that. A battery is trying to go in that direction. This is a battery. This thing is a battery. So by lowering the concentration of the Al, what am I doing? Am I causing this battery to create more voltage, meaning always making more products, or not? That's what it's basically saying. So by answering the question in the format, will this increase, decrease, or remain the same for the cell voltage? It will increase. And you can simply say it will increase because it will create more products. I mean, you can use Le Chatelier's with this. That's how I actually would do that. Just look at the equation. They give it to you for a reason. There's all sorts of other things you can look at. Well, this goes smaller, so that means that there's more room. Guys, this is how you could do it with the diagram. There's more space, saturated space, like there's open unsaturated solution of the Al, so more of the aluminum can go in there and drive more electrons to the other side. It's another way you could think of it. But that's a bigger leap. Okay, so I've already explained that. I'm not going to write that one out for you. So I would just use the equation. I appreciate it. Again, you got to go. We have 3 more just equations. I need you, it's not in this format anymore, but I need you to just know how to do one of these for sure, especially. So let's get to the last one, and we are done. In the past, they actually had equation sections. They used to have 8, you pick 5. Then they had 3, you had to do them all. Now they're like, let's just not do it. So I missed them, but it was really stressful for a lot of people. So let's talk about it. It's usually net ionic, so we need to talk about it. That's why we did that first worksheet, substances. So if they're ions, they need to be in ion form. So let's just look at this. So a piece of solid strontium carbonate is dropped into a 0.1 molar solution of HCl. All right, so I'm going to kind of guide you a little bit. Strontium carbonate, SR, carbonate CO3. You do need to know a little bit about units. So charges, so I got SR 2 plus and CO3 2 minus. So that one works out really well. Now, if you're having problems, let's just talk about this. And I'm going to cross some stuff off. So if you want to wait for me, you can. But that's a strong acid. So that's how it actually breaks apart. But your instinct right away with strong acids, just H+. Strong base, OH minus. So what do strong acids do? Strong acids attack. Strong acids break apart. So H's. And this is something that I'm going to make sure you have just the most basic knowledge possible. But how an acid attacks a salt is it will break it apart. Okay? And then you need to just reassess what goes back in there. So the SR is going to break apart. So now think about this. I have the SR2 plus floating around. Okay? Now I have this H plus. I have this CO3. And I have this Cl minus. Okay? Like those are all the things kind of floating around. Okay, well, something's going to come together. Something has to come together, or else you can't write anything. So usually what happens is the acid's going to try to make something new. So you could argue, and that could be an H2CO3. There's two answers to this one. But just for the sake of you seeing how this works today, this is not the one that I'm as worried about for you. That's actually what's going to be made. You could argue that this makes H2 and CO3 2 minus, which we will talk about in a second. And then, so if this is a natural couple, because this kind of looks like a double replacement, SR and Cl would go together. But halogens are very soluble, and it's already aqueous. So if I would write them both like this, I'll say this again. This is a weak acid, that's why it stays together. What can I do? And this one is not the one that you need to have down as much. What happens? Net ionic equations. What do I need to do? That's gone. That is gone. So, that would be it. Now, here's the problem. That's one answer to this. It says indicate one thing that would be observed as the reaction occurs. Okay. The thing is, you can answer this in a couple ways. This, you could have assumed maybe also made this. That's carbonic acid. And I'm just giving you, any background's good. What could that make? What could carbonic acid make? Think of carbonation. CO2 and H2O, right? Wouldn't that naturally be those, I mean, just purely balanced. It doesn't even mean anything. So, whenever you say observed, we'll fly through these other two. This one's probably the most complicated one. You're either looking at a precipitate, a gas, or a color change, or heat. Those are those four things, right? So I don't know if there's heat. There probably is, a little bit. But there is something I can definitely talk about. There probably would have been gas at some point because of this. This is the one that I would lean towards because of that. So there would be gas or bubbles. And unfortunately, if you didn't make that leap, I don't know. You're going to have to try to figure something out off of that one. So carbonic acid makes CO2. Again, don't let that one rattle you completely if not, you're not understanding. Again, of the three, by far the most complicated and off compared to the other two. Here we go. Magnesium metal. This one we're going to be able to get. So Mg, strongly heated in oxygen gas. If you want to put a little thing like that, that's great. That means heat or light, or you can write heat. So if I'm putting that's it. That's all it says. So if I have no other options, what am I doing? I'm putting things together, right? So magnesium and oxygen come together. Every time I make a new compound, I got to check my charges. So hopefully this makes sense that it would make that. Right? It's going to make one compound. Guys, I've done this a ton of times. It's the magnesium. You put it in a Bunsen burner. You balance it. What is the oxidation number of magnesium before the reaction occurs, and what is the oxidation number of the magnesium after the reaction is complete? When things are by themselves, the oxidation number is 0. Afterwards, it's the charge. If it's in something, what's the charge of magnesium when it's binding with something else? 2 plus. Done. Okay? This one, though, is the most important one to me. And this one comes up all the time. Not this exact one, but this type. So please, hone in on this one. It's a solution of nickel 2 chloride is added to a solution of sodium hydroxide, forming a precipitate. This is a classic double replacement. Most of you should be able to get this eventually without writing everything I'm about to write. In the past, when you guys were in chapter 4, you did this a lot faster. Okay? So, here we go. Nickel 2 chloride. It's a solution. They have to be broken up. Added to sodium hydroxide solution, forming a precipitate. So now, here's the trick. If it's not in a precipitate, it's still going to be ions. That means they're just going to cancel. So what I taught you guys in the beginning of the year is write the precipitate first and then write the ions that made it. So what is the precipitate? What's the formula? When it makes new partners, what's it going to be? The NiOH2. Got to crisscross. Okay? Because that's there, you're going to still have Na plus and Cl minus floating around. Why? Because they're still just aqueous solutions. So I can just cancel those out. and I balance it. If you want, like, wait, I don't get it. It would have this, but they would still be ions, so they'd be gone. So suggestion, and I see this every year in some sort of problem, it'll say, write the net ionic equation of the precipitation reaction. Whatever the precipitate is, write the ions that are made from it. You still got to balance it. Final quick question. It says, if equal volumes of the 1.0 molar nickel chloride and the 1.0 molar sodium hydroxide are used, what ion is present in the solution in the highest concentration after the precipitate forms? After the precipitate forms. So, if you actually look at this, this is the key to this. Because this is that, and this is that. Just by looking at that, which one has the highest
Leah Grant, if you're in the building, please call 6729.
highest concentration? It means it has to be an ion. So the ion that's not used up would be the highest concentration. So these guys are not in the game. So what is the answer? Just the ion. Which ion would have the highest concentration? The chloride, because it would be double all concentrations, correct? So the Cl, it doesn't ask for a calculation. That would be the stuff that's floating around in the highest concentrations. Okay. I know we went through a lot. I hope a lot of things are looking more familiar. Okay. So, thank you. That is review session 1.